Okay, so you are going to use the standpoint for Chapter-1 and also for Chapter-3. For Chapter-3, you start the CRE, first CRE for Chapter-3 on the standpoint on the number 26. Yeah, so 26 will be the CRE for 3.1. Understand? Yeah, 26. The 26 is the number what we call CRE 3.1. So keep a good track of which one for which CRE. Okay, so we are going to start on the Chapter-3. Chapter-3. So we first studied Chapter-3 today for a few sections. Then we will do the second lab. Right? The second lab is CSI. So you should be able to get the level menu from the cameras. And yeah.
For some reason I'm not able to access the manual.
Oh, that's okay. So you can share with your group members. Or I can. I see what's the problem. Right, and also remind you a couple of things. First is keep tracking the schedule on the cameras. See what quiz is due on what day. I think this Sunday you will have the quiz for chapter 2. Right? So don't forget. You should start a little early. Don't wait until the last minute. Right? So you have plenty of time and plenty of try. You can try 5 times. And the second thing I want to remind you is turn in the lab report 1 week from the day we do the lab. So today you are turning in the lab report for the first lab, which is the density. Right? Any questions? Good. So then we will start on Chapter-3. Chapter-3 is about moleculars, compound, and chemical equations. So we do elements has one type of atoms, not exactly because we have different isotopes. And most of the atom is not that inactive, except a few of those smaller noble gas like helium, neons. So most of the atoms are very active. So usually they do not exist as those very nice atoms. So they will either exist as ions by themselves, like sodium in sea waters. You will see that sodium Na exists as Na+. So that is one example. And then a lot of them are also combine with something else or with themselves to produce compound or molecular elements. So even though we only have a few different type of elements, but we can use them and make a lot of different combinations, just like you can use 26 letters, make a lot of English words. You can use those atoms and combine to make a lot of compound. So once that happens, the properties of the compound are totally different from the properties of those constituent elements. So that means there will be a chemical change when the elements, when the atoms turn into compound. Let's see, one like a typical example is we can combine hydrogen atoms with oxygen atoms, produce water molecules. Before the change, before we make the water molecules, we have the the hydrogen elements, and which exists not as individual atoms, but each two H atom combine into a H molecule. You can see from this picture, you have two of those H atoms combined together. That's still an element because you only have one type of atom. And similarly, the oxygen, they also do not exist as one atom by themselves. So two oxygen atoms combined together produce oxygen O2 molecular, are still elements. And this is before we combine element and element into compound. In this picture, just tell us most of the atoms are so active. So even before they combine with different atoms, they combine with the same kind and produce a molecular, but those molecules still are elemental molecules. Now if you put those two together and starting the chemical reaction, usually you can start with a spark, and that can produce a compound. So H and O combine with some ratios. In this particular example, you will have 1O combined with 2H and produce a very well-defined structure and ratios. You have this H2O, and which is the typical water. So from this example, you can see the change, the dramatic change. So before the chemical reaction, we have two elements, and we have hydrogen gas, oxygen gas, and they have their own physical properties, chemical properties. Physical property, for example, boiling point for H2 is negative 253 Celsius. Boiling point for O2 is negative 183 Celsius. But once that combine into a compound, and one example of change is the physical property, is the boiling point of water become 100 degrees Celsius. There's some other change, obviously too, there's chemical property change. But from this physical property, you can see the dramatic change. Right. So I think I put this slide in this way. It's kind of wanting you to review what we studied in chapter 1. So in chapter 1, we learn how to classify matters. We know matter, the first line classify matter according to the composition is pure substance and a mixture. Okay, so this obviously still talk about the change from element to the compound, but I want you to be able to identify these two materials. So on the left side, we have this picture, and by what we learned in chapter 1, we can see what kind of material is this material in the inside of this container. Inside the container, you want to classify this matter. Remember, we asked like a few questions. The first question we want to ask is this material has only one type of atom? If it is yes, it's elements. Right? If no, it will be either compound or mixtures. Right? So therefore, let's first identify in this picture inside this container, do we have only one type of atom? No, we have red and we have white. So therefore, it's not an element. So therefore, can be either a compound or a mixture. So then the second question is that all those different type of atoms combine into only one type of molecule. If it is yes, then we have a compound. Otherwise, we'll have a mixture. So therefore, this material inside this container is what? The mixture. Right. So then you can, it's precisely is a mixture of two elements. So we have elemental hydrogen. So this is hydrogen, and then we have element oxygen. So we have these two elements, which is not combined yet into only one type of molecule. So therefore, we call that a mixture. Now, after we combine that, usually you will see some of those video or some of those demonstrations. You can have this container, then you just take like one of those flame nearby, ignite, then boom, then the chemical reaction happens. So then all those H2 and O2, if you mix with the right ratios, so they will combine into H2O. And then you will produce those kind of pictures. Right? So in this picture, we know the material become what? It's a compound. Okay? Again, after that, like the color patterns, do we have like only one type of atom? No, so therefore not elements. And then you can examine, do all those different type of atoms combine into only one type of molecule? You say yes, because all those model here representing H2O. And so this, again, just emphasize what we learned in the last slide. So we can see the most of the atoms are very active, so they can combine into compound, and you can combine H and O into water, or can combine H and O into hydrogen peroxide. But in this example, we see we have water. So then, what kind of force? What do those atoms use to stack together to combine into molecules or into some of those compounds in general? What we call that is a chemical bond. So chemical bond is not really strange to most of you if you study chemistry. So they representing actually ultimately is the attractive force between those electrical charge. And we know that is one fundamental force, one of those four fundamental forces in nature. Gravitational force is one, electrical force is another one, and then those strong nuclear force is another one. So you have those common electrical charge in the atom, because we know what we studied in chapter 2. In the nucleus, we have the positive charge, which was on the protons, and we also have neutrons in the nucleus, but that is neutral. Then outside, we have the electron, which has opposite charge as the proton. And no matter where they are and how they distribute, you know that the electron will carry the negative charge. So therefore, so somehow those negative charge on electron can attract into those positive charge in the nucleus. So that is the ultimate resource for the chemical bond. Electrical forces of attraction between atoms, this is actually the so-called chemical bond. And so then you can have those attractions between those electrical forces, but ultimately, as we said, it will come from the proton and electrons. So then, according to where are those electrons and where are those protons? Proton obviously will be in the nucleus. So pretty much where are those electrons and how the electron and creating those attractive forces to the protons. So we can classify the bond into different types. So there are many details types of chemical bond, but in this chapter we will start with two very, very common ones. One is ionic, the other one is covalent. And covalent, you will have different covalent. You can have those network covalent, and then you have also some other chemical bond like a metallic bond. But the two most important and most common ones are these two, ionic bond and the covalent bond. So that depends on how the electron creates those attractions. So in one type is the ionic bond. Ionic bond which means the electrons are somehow transferred from one atom to another atom. Then, as we know, if that happens, as we study in Chapter-2, when the electron transfer, which means some atom lost electron, some atom gain electron. If those atoms lost electron, become cations. If those atoms, or a group of atoms in general, gain electrons, they become anions. So this will be the ionic bond, the one type. So we studied those bond type, and we're also going to study in this chapter those compound type. We call them ionic compound and molecular compound. So in this chapter, we just study kind of like one like definition. So we will say like any metal, and we know those metal in the periodic table is on the left side, and combined with any of those non-metal, you will produce, or you just call that ionic compound, even though later on in the other chapters we probably will retreating back and we say that probably not that precise, but we will just stick with what the book said. So this type of bond, ionic bond, you will typically find out, we can find out in those ionic compound, and so that's generally found when metal atoms bonded to those non-metal atoms. And also include one special type or one special group of non-metal atoms, includes anything has this guy in it, ammonium ion, NH4. Okay? So whenever you see this NH4 in your formula or in your name for the compound, even though all those atoms here is non-metals, for example, you can take this NH4 and combine with chlorine, you get this ammonium chloride, and that's also ionic compound, even though we don't have metal in it. And so this is one like a very, very dramatic exception to this usual pattern, metal plus non-metal produce ionic compound. There are some other similar ion as this, so sometimes I write the plus out, and in this formula, when you write the formula for the compound, you don't write the plus or negative, but in your mind, you will know the NH4 together somehow lost one electron, become a cation. There are some other ions similar as this. You can replace H by some other atoms or group of atoms, so you still have something like a positive charge on this nitrogen atom. Well, most of the positive charge on nitrogen atom, but as I said, this group carry this positive charge. So there's other type, covalent bond, and it results when two atoms share some of their electrons, and they don't have to. The atoms don't have to share all their electrons, and they might share like 2, they might share 4, they might share 6. So whenever they share some electrons, and you will call them, there is a chemical bond between them. Right? I mean, when they share to some good extent, and you produce those molecules. And so generally found when those non-metal atoms bonding together, then similar line. Okay, so not all those non-metal atoms bonding together will produce those covalent bond. So if you follow what I write on that exception, you can see it accepts when you see this guy in your formula. That's straightforward. Same as what we say that include ammonium ion in the ionic bond. So therefore, you accept this kind of ammonium ion in the formula because you have that everything here is non-metal, but not all the bond here is covalent. So there are some bond in this formula that is covalent, but some bond here that is ionic. So you can see this two type of bond and use our general rule and just try to see some of those exceptions. So our general rule is between metal and non-metal or the ionic, and between non-metal and non-metal or the covalent, but with this exception, ammonium ion. Right. So then, usually the covalent bond is weaker than the ionic bond. So this picture gives you some of those reasons. Because when you share electrons between two atoms, so you still not isolate or fix those electrons at one atom, so therefore they can share at different place. If that electron was shared between the two atoms, and exactly on the line between the two atoms, so that will produce the maximum result, that will produce the maximum attraction between the electron, the protons. But the electron is not fixed at one place as you will study in Chapter 7. So the electron is always moving. They are not moving at one trajectory like the moving of Earth around the sun. They are moving just at a certain space. So therefore, they can, even though they are shared, they still can be up, down, or even more dramatically, they can even not in between the two atoms. Therefore, because of all those possibilities, compared with the ionic bond, if you have the sodium ion and Cl magnetic ion, so then you can say this electron, some of those extra electron was lost by the sodium, where we pretty much spanning this place. So therefore, you will see that the 2 points charge, the positive here and negative here, is a little like better defined. So the Na is always plus and Cl always negative. So therefore, the possibility of those attractions is better than the attractions for the covalent bond. So here are the examples of this few different type of bond, and then also show us the change of those process. You can see that the sodium metal has the metallic bond, and then this chlorine gas, in between the chlorine atom, that is a covalent bond. So in the chemical reaction, the sodium atom lost electrons, and those chlorine atom gain electrons. So as a result, the sodium atom become the Na plus cations, the chlorine atom become chloride anions, and then you will see the attraction between the sodium ion, the small one, and then the chlorine ion, the large one, is the so-called ionic bond. And those bonds is very strong because you know that it's a little difficult to break the bond between the sodium ion, chloride ion, because you know the melting point of table source is relatively high. Right. So now we know we have a different type of bond and how we representing those compounds we produce. Because when we have different type of atoms can combine into compound, and two typical forces combine them into compound. One is ionic bond, the other one is the covalent bond. So there are a few different ways. There's a model, formula, and here we see there are a few formula and a couple of model. We have the so-called molecular formula, structural formula. So all those models or the formulas will tell you what type of atoms in the compound. So then, depending on what we use, we'll have some other information. We might also know what is the geometry, what is the spatial arrangement of those atoms. And we might know like the angles between those atoms. And we also might know like exactly how much atoms are there, how much H are there, how much carbon are there, and so on. And so then in this four like those examples, and we miss one, but you will see that on the next slide are the so-called empirical formula. Empirical formula will be the formula that you can use for those ionic compound, because in the ionic compound, so even though you mix different type of atoms, and you not really produce the so-called molecules. Molecular straightforward definition is a group of atoms stuck together. They will not change in the, for example, in some of those typical physical processes. And empirical formula, so that's another way to represent those compounds. So we will study each of those formula and each of those model maybe in little details. So let us see what we mean by those empirical formula first. The empirical formula is the formula you can only use for those ionic compounds. You don't call those ionic compound a molecular formula. So then for the molecular compound, you can have both. You can have the molecular, you can have the molecular formula for the molecular compound. You can also have the empirical formula for the molecular compound. Sometimes for the molecular compound, the molecular formula and the empirical formula may be the same. But if I don't tell you they are the same, then you should clearly have these two different concepts in your mind. Empirical formula, if I don't tell you that is also same for the molecular formula for those molecular compounds, what you can tell me for sure is what type of atom in the compound, but you cannot tell me for sure how many are there. So empirical formula just tell you the simplest ratio of the atoms in the compound. And as I said before, the formula for the ionic compound, the only one formula is the empirical formula. So if you know your compound is ionic, so you don't call that a molecular formula. The reason is for the ionic compound, you don't have really those pair or like few atoms together, always stuck together for most of the process that the so-called molecules. So then compare the empirical formula with the molecular formula. Molecular formula, it will still tell you the ratio. Obviously, you can tell the ratio too, because you can simplify the ratio into the simplest ratio. So in addition to that, molecular formula tell you not only the ratio, but it means not only what type of atom in the compound, also tell you exactly or precisely the number of their atoms. And so if I tell you this is the molecular formula for the number CH4 for the cooking gas methane, which means you will know for sure in each one methane molecule you will have one carbon 4H. Even though for this particular molecular compound, the molecular formula is CH4, the empirical formula will be also CH4, but this ratio 1 to 4 is the simplest ratio. But if I don't tell you this is the molecular formula for this CH4, then you cannot tell me for sure how many atoms are there. And both molecular formula and empirical formula will not tell you the order of attachment or the shape, will not tell you directly. But if you have some experience, because later on you will see in chapter 9, chapter 10, we write methane as CH4, then we will write the Lewis structure, then we're like predicting from the Lewis structure what is the geometry of these 5 atoms in space. And then from those informations, you can infer it. You can just think about what is the structure. But if you don't use your experience just by looking at this CH4, and obviously you don't know what are the shape, what is the geometries. Right, now in this chapter form, you can see the title of this chapter, atoms, molecules, and equations. So therefore, we're going to spend a lot of time to study those different formulas, and we're going to see different way of getting those formulas, or exchange those different formulas. So now this first exercise is very straightforward. That means if I give you molecular formula, and you can get the empirical formula. And then later on in the other sections, I will give you some other information and ask you to tell me, you do some work and calculate what is the empirical formula from the information I give to you, and what is the molecular formula from the information I give to you. So this is examples. Again, the examples is getting the empirical formula or compare the empirical formula with the molecular formula. So I have a few examples. One example is a hydrogen peroxide molecular formula. Probably most of you know what is H2O. Hydrogen peroxide, but not that straightforward. Hydrogen peroxide H2O2, and this is the so-called molecular formula. So I tell you what is the molecular formula of hydrogen peroxide. I will tell you H2 and O2, which means for each one molecule of hydrogen peroxide, there are 2 H and 2 O. So that tell you couple of information, tell you what are in that compound. Hydrogen are in there, oxygen are in there, and also tell you precisely for each one molecule how many hydrogen atoms are there, 2, how many oxygen atoms are there, 2. But you can get another type of formula called the empirical formula. Empirical formula can apply to any compound. Okay? But for the ionic compound, you don't have the molecular formula. You only have that empirical formula. Right? So therefore, the empirical formula you can get in this example is from the molecular formula. To get that, you just examine what are the subscripts for all those atoms, all the group of atoms, and then find out the largest common number for those numbers. Then use the largest common number divide into all those numbers. Those numbers here, we call them subscripts. So there's 2 here, and 2 here. So here we call that subscript. And this is the number you will see quite often in the formula, maybe the molecular formula or the empirical formula, tell you how many atoms are there, or how many group of those atoms are there. So you have a 2O, because this 2 is right after this O, you have a 2H, that's outside after H, and that tells us precisely in one molecule of hydrogen peroxide, and both numbers can be divided very nicely by 2, so therefore you can just reduce 2 and 2 into 1 and 1. Now 1 and 1, that will be our empirical formula. Right. Now the example is benzene. Benzene is a typical organic compound, and you have that 2 type of atom in there again, or 2 type of element in there again. You have the carbon element, hydrogen element. And here again, we just compare these 2 type of formula. We have the molecular formula, empirical formula, molecular formula is C6H6. That means for each benzene molecule, so here is the model for the benzene molecule. Benzene molecule is very, very important in chemistry. And you can see these 6 carbons produce a cyclic structure, a hexagon, and then this 6H is bonding to 6 different carbons, and the molecular formula tell you we have 6 carbons, 6H, slightly, and also tell us we have 2 type of atom. Then you can reduce that into C1H1, and then the result after you reduce, and that becomes the empirical formula. Okay? So therefore, the empirical formula, if you don't know the molecular formula there, you will just only say what in the binding is carbon and H, and what are the ratio of those atoms between carbon and H is 1 to 1. Now, how many carbon are there, how many H are there in one binding molecule? If you don't know the molecular formula, if you just look about it as CH, you don't know how much carbon are there, right? There are many similar examples. So another example is glucose. Glucose is a sort of a monosaccharide, those carbohydrates. That means some of those sugars is one example of those carbohydrates. So that means you will have the oxygen in it, you have carbon in it, and hydrogen in it. So that is a molecular compound. You can represent those compounds by the model, by the molecular formula, by the empirical formula. Molecular formula with C6H12O6. That tells you have 3 different types of elements in it. You have carbon, H, and O. But if I tell you this is the molecular formula, then you will also know precisely. In each one, glucose is very simple. Those carbohydrates is very easily digest because you know that you don't have to breaking apart those chemical bonds. You can just you can get those from like some those fruit, glucose apples, or have those glucose. So then you can reduce the molecular formula, but that tell you how many atoms are there. But sometimes you can just say that you only like consider what are the ratios. So you can just say what are the largest numbers, 6 and 12 and 6. So all can be divisible by 6. Therefore, you can reduce that into 1, 2, and 1. Right. So that probably will be one of the simplest problems you can solve. If I give you the molecular formula and you want to get the empirical formula, right? You just like find out the largest number that divide exactly into all the subscripts. The subscripts are those numbers, the lower right corner. That will tell you how many atoms in the formulas. Right. So what will be the empirical formula for that C4H8? So one of those hydrocarbons have those organic compound. So what will be the empirical formula for that C4H8? So we have a C4 and H8. So we have 2 subscripts in this formula. We have a number 4. We have a number 8. So what you do, you just find out what will be the largest number that you can use to divide into both of these 2 numbers. What will be the largest number to divide into 4 and 8? 4. So you take 4 divided by 4, and then you will get C1. Right? So that's C1. That comes from, you take 4 divided by 4. Now what will be the number for H? So you will take 8 divided by 4, that will become 2. 1, usually you can omit by convention. So when you say 1, that means that equivalent to CH2. And then this, we call this is the what formula? Empirical formula. All right. Any questions? Okay, so that's the first one. Now let's do I think you can be able to do the other one. All right. So the other one is B2H6, and I tell you this is our molecular formula. If I tell you this is the molecular formula, then you will tell me for sure in each one of those molecular, we call that B2H4H6, is called the boron. Is a very, very important organic reactant. So this general chemistry, you will gradually get familiar with some of those compounds you can later can use in some of those other class. B286. It's a very, very important compound. And you have that, you can change some of those organic into alcohols and so on. It's very interesting. So right now we have this B286. It's a molecular formula. So for each one of these, we'll have 2 boron and 6 H. So what will be the empirical formula for this? Right, so we'll have B, the 2 is divisible by 2, and then that 6 is divisible by 2, and you divide that, it will become 3. Right? Right, so from these 2 examples, you can see if I give you the molecular formula and you find out the large number, you can reduce into those. Right. So the next one is C and Cl4. And I tell you, this is also our molecular formula. Okay? Molecular formula, if I tell you this is the molecular formula, so therefore you can tell me for sure what element in there, what element in this CCl4. The carbon tetrachloride is very, very important organic solvent. And people used to do like the dry cleaning. Yes. So if you have some of those very nice dress or clothes you want dry cleaning, used to use that, but later on we changed that because it's kind of like carcinogen. Right. So if I tell you this for sure is a molecular formula, then you can tell me 2 things for sure. One thing for sure is what type of atom are there. We know there's carbon in there. What else in there? Carbon in there. The second thing for sure is you can tell me precisely in each one of these molecular how many carbon are there. 1 carbon. How many Cl are there? 4. Okay? Right. Now, what will be the empirical formula for this carbon tetrachloride? That's the same, right? So sometimes the molecular formula, the empirical formula might come out like the same. Right? But if you were told or you were given the empirical formula, even though for this example it's the same as the molecular formula, but if you don't know that's also the molecular formula, and you don't know you cannot tell me for sure. For each molecule there is 1 carbon and 4 Cl. Right? So then you can get this C and Cl4 same for the empirical formula. Alright, so this you will put on the scantron 26. Okay? For that scantron you used for chapter 1. Right? For chapter 1, for chapter 1, you use the first few. Now you can see this for chapter 3. Do you get the scantron back?
Okay.
For chapter 1?
No, I didn't get the chapter 1 back. I have chapter 2 right here.
Chapter 2.
Yeah.
We have the scantron for chapter 1. Will you turn in?
Yeah, it's in the news.
Is this you? Okay. Welcome. So if you did not turn in the scantron for chapter 2, I think probably because you did not bring the scantron like Tuesday for chapter 2, then you can turn in. Now for this one in chapter 3, so you use scantron for chapter 1, and for this first CRE, you put on the 26. Alright, what do you think? What will be the, maybe we can do something like this. Right?
Is it E?
You say what is it, D?
E.
D or E. Okay. Right?
No, it's
So the answer is E, right?
Yeah.
Any questions? So that's, as I said, will be the very good practice. So I give you 3 molecular formula, and then you can see in the molecular formula, all those guys, we call them the empirical formula, And you will have those chemical symbols for different elements, Hg for mercury, Cl for chlorine, and H for hydrogen. Then you also have those subscripts. The subscript will tell you how many atoms in that formula, but in related, is that also the number for the molecule that depends on what formula you have. Right? You can get the empirical formula from molecular formula by reduce those subscripts into a simpler ratio. Now after we study this first few slides of this Chapter-3, so we know some of those compound is a molecular compound, some of those compound is ionic compound, and you can do a similar extension for those elements, because we know the element is the type of matter that has the same type of atom in it. So that only tell you the atom in the material are the same or not. If the atom in the material are the same, you know your matter or your material is the element. So then, what way those atoms exist in the atom? I mean, in the material. Do they exist as one by one? It's kind of one by one. Like sometimes you also have some of those combinations. But what we say here, for example, like metal, they really, in some sense, they don't exist as like one metal atom, another metal atom. You still have this bulk material. Right? But what we see here is if you have those elements, if the element, you can see like those elements produce like one by one molecular from 2 same atom, maybe from 4 same atom, or from 8 same atom. Those kind of elements, and we give them a special name. We still call them elements, but if you can see, you call them molecular elements. So we still use the same question to classify whether our material is element or compound. So that is still like what we learned in Chapter 1. So if you have those only one type of atom in your material, then you know your material will be element. If you only have one type of molecular with different atom in it, then you know your material is compound. Right? So now we see we have some new definition here, molecular elements, which means those atoms in the elements, they exist as those molecules. And those molecular is a bit different than those molecular, because those molecular is a molecular compound. In this molecular, you have a different type of atom. In this molecular, you have the same type of atom. So even though you have molecular, I have molecular, so molecular is not the key word to classify whether you have element or compound. So then some of those materials, a good example of those materials, they really exist as one by one atom are those noble gas. Noble gas like those you get from like those helium or neon in the street light, and so then you can see they exist. Really, there is not too much interactions between a neon atom, another neon atom, right? Right. So now we again we have these two new concepts. Elements can be molecular elements, can be atomic elements, and a similar idea about compound. Compound, as we know, is a combination of different type of atom. Then we know what type of force or what type of bond combine those different atoms. According to that, and we say those compounds can be moleculars or be ionic. Molecular compound, which means you only have those covalent bond, and for those ionic compound, you will have those, for sure you will have those ionic bond in it, and you might also have those covalent bond in it. But as long as you have those ionic bond in it, we'll call them ionic compound. So hang on there, later on we'll summarize those different type of compound and what chemical bond are possible in there and what's in those compounds. Do you have those atoms bonding together, molecules, or do you have those ions in there? Right? So right now we see this is our new definition for the compound and element. Right. So let's finish this slide. So we can see. So this is about some elements. Right? Elements whose particles are single atoms. For example, noble gases, that is precise. Or metals, metal not that precise because in metal you will see you still have those atoms down the chain in something else, but those atoms really they kind of like a gigantic molecule, but we call them like just one by one atoms. So those kind of elements is what you call this kind of elements? Atomic elements. Yeah, so that is the name. Well, let's see some examples. Do you know some examples of those atomic elements? What kind of element is the example of atomic element? I give you some of those groupers. So I give you two groupers. One grouper is what? Noble gas. Other grouper is what? And also give me some examples of noble gas. Neon, neon, right? Argon, yeah, sodium will be the metal. Yeah. Sodium will be the metal. There's some other metals, calcium, right? Some of those Cu. Right. So all those are good examples of atomic elements. So there's two other groups. You can use any of those elements in these two other groups. Some of noble gas, some of those metals. Now this second type is also the elements. Now these elements whose particle, are multiple same atom molecular. So you have to see there's molecular in it, but what type of molecular? Those molecular, they have the same type of atom. So therefore, you still have this key word element in it. And otherwise, if you have a different type of atom in your material, you might have compound or mixture or something, right? You don't have element. You don't have the pure element. You have a different type of atom. Now, what do you call this? I also give you some of those examples because you're not familiar with those yet. So I'll say that some of those like the S8 is really exists in sulfide. So you see that if you have like a chunk of sulfur, so if you have a block of sulfur, you know that's S in it, and the S exists as what? It's not really like one sulfur atom, another sulfur atom like those noble gas. It's actually 8 sulfur atom like produce kind of like cyclical structure, and that's the sulfur molecule, right? And phosphorus, similar phosphorus, the formula is P4, but you will see that maybe there are different color of phosphorus. There's red one, there's pink one, depending on the crystal for these 4 atoms combined together, produce like a lot of materials. Right? So these are the 2 examples of those another type of elements. And in general, what do we call those type of elements? Right? So these are molecular elements. Right? So for these 2 examples, that's common. I think from your previous chemistry class, I want you to know this. In this chemistry class, there are 7 of those diatomic elements. Diatomic elements, this name is not that straightforward. That means in these 7 elements, 7 common diatomic elements, what do we mean by the diatomic? Which means they will exist at the usual conditions, means normal temperature, like room temperature, and the normal pressures. So they will exist as two atoms together produce a molecule, but in that molecule you only have one type of atoms, diatomic elements. And there are 7 of that. I think some of you already know that. So you are examining this periodic table. So you're starting from the leftmost, some of the elements. For example, H is the leftmost, and so then H will exist as the usual conditions, like room temperature, room pressures, is H2. Another one H atom, another H atom in a gas of hydrogen gas is really 2 H atoms combined together produce an H2 molecule. So that's one of the 7. And then the next one is the nitrogen gas, N2. Nitrogen gas is the most abundant one in the air. So then, do the nitrogen exist as one N, another N, like normal gas neon? No. So usual condition, the nitrogen gas will be N2 together. And then another major component in the air is oxygen gas. So you have that O is O2. And then fluorine F2. So we have 4 here. So we try to remember this number 7, and because we have 7 here, and their location in the periodic table altogether is roughly also resembling that our Arabic number 7. See, this looks like 7. Right. So try to memorize that. That is important. And sometime I will tell you we have we have an example of oxygen gas, or we have an example of chlorine gas, and then you will know what is the formula of chlorine gas. So when you do the calculation, formula is very important because as we studied briefly in the Chapter 2, so we have to use like the molar mass to convert from gram to mole, from mole to grams. And to get the molar mass precisely, you have to know how many atoms are there, what atoms are there, right? So if I tell you it's a chlorine gas, I did not tell you straightforward chlorine gas is Cl2, but you know if I refer to chlorine gas, so therefore you know it's a Cl2, not a Cl, not a Cl3. Now that's what I tell you to hang on there. So we are going to have more details about the 2 different types of compound. So according to like what we studied in the first few slides, we see compound can be ionic and molecular. So then let's see these few common properties. What I want to see is what element in there. Those are what common questions. So sometimes you're asking like in the ionic compound, what is the common constituents? And then what bonds are there? And what are their particles? In the material, what are the particles they exist? Do they have ions? Do they have molecules? And we'll see some of those examples. Right. So let's examine the first one first. We are going to examine this ionic compound first. Will you tell me what element is commonly in the ionic compound? Metal plus what? Non-metal. Okay. Now also includes that one. Right? Metal plus non-metal, that is the majority for most of those ionic compounds. That is true. You just say. Therefore, when you're looking for the ionic compound, you're looking for the metal. Okay? But again, according to this chapter, so later on in the other chapters, we will see our definition probably not that sharp cutting line. So just right now, just know we have this chapter. Okay? Right. So metal plus non-metal, that's the first thing you study. That's the first thing you're looking for. If you see metal in it, then you know for sure for this chapter. Your compound is ionic, but don't stop at that place. So you'll say, even though your material don't have any metal in it, you just do like a second step, where it means you try to looking for this guy in your compound or in your formula. Right? So if you have this innate, and maybe just simply like that, or maybe like a little bit like what we see here, like just NH4, that is clear, you have NH4 innate. But in some other compound, you might have a little bit like here, so I will write NH4, and then parentheses, and then I will add in a subscript, right? And then I will put like another, also very complicated ion. You see this is ammonium carbonate, it's a very, very common fertilizer. So you will see, by using this compound, you want to classify what type of compound, this obviously is a compound, because there are many, many different type of atom in it. What do you call this material? Obviously not element. Is this a mixture? Why you say, first not a mixture, because if I tell you all those different atoms here, I only have only one type of molecular, or this formula unit, therefore it's not a mixture of those different elements. So then you will say, what kind of compound is this? Right? So material can use this as either element, compound, or mixture. Even though mixture in details can be homogeneous, heterogeneous, but at least you know these are three major types. Right? And so now you will say this. Do we have metal innate? If we have metal innate, like one common example of metal, as you said, is sodium. If I have a sodium and I have sodium, let's say Cl, that's the table salt. So this one, what kind of compound is this? Ionic, yes, looking for metal, so therefore ionic. Now for this one, you will say, do a similar, you're looking for metal. Do we have metal innate? No, all those elements here is non-metal. But I said that, if you already identify this ionic, you don't have to examine this guy, right? If you don't have metal innate, so therefore continue the second step. Do we have that NH4 innate? Yes. In that one we have only one NH4, in this one we have two NH4. So as long as I have one, no matter you have two or three, so therefore your compound is ionic. Right? So that's usually easy to forget because you usually go by the good patterns. So most of the ion compound in metal, non-metal, so you forget those exceptions. Right? So then next is about what bond innate. Do we have ionic bond innate, or do we have those covalent bond innate? The ionic compound, obviously you will have those ionic bond innate, but depend on ion, not only you will have those ionic bond innate, you might also have the covalent bond innate. But for sure, the covalent bond might be there, might not be there, but the ionic bond will be always there, according to this chapter, if your compound is ionic. So ionic bonds are there for sure, or both. Now or both, that means depend on what ion in there. And I think I have some of those good examples here. So all those compounds here is ionic. We know this is ionic. Even though this don't have metal in it, we don't have that in it. This one don't have metal in it, but we also have the ammonium ion NH4 in it, so therefore those ionic. That's also ionic. We don't have metal in it. Now this will give us some good idea. What bond are in there? So what bond in this one? What bonds or what bond in this one? Because it's ionic, so therefore you know if you already identify your material is ionic compound, you will tell me you will have that ionic bond in it, but you might have more. You might also have the other one called the covalent. Depending on what ion are there. If the ion in your ionic compound are those monoatomic ion, then you will only have the ionic bond. if the ion in your ionic compound are those polyatomic ion, not only this one in it, and as long as you have those polyatomic ion, then you know you not only have those ionic bond, you also have the covalent bond. Right? So this one has ionic bond. Ionic bond is between the NH4 plus and Cl1 negative. So if I just not really make some sense, I just circle these two because this is one ion, the cation, the other one is the anion. So then the attraction between these two is an ionic bond. And this is simple, there's only one atom in it, so therefore you don't have any attraction, just one chlorine, like again one extra electron become chloride. Right? Now here this is the ion, and this ion is the polyatomic, and in this ion you have like 5 atoms in it. Now how these 5 atoms combine together produce this ion, or what is the force to attracting these 5 atoms together produce this ion? So those the so-called polyatomic ion. You can study that in more details in chapter 9, chapter 10. And for this one, you will see the bond between these 5 atoms is like this. So you have a nitrogen atom in the middle, and then you have 4H. All the 4H is a single bond bonded to the N, and you have this structure for that NH4. Okay? So now the bond between N and H, each pair of N and H is covalent. Alright, so this is our covalent bond. Okay? So therefore, overall, in this type of compound, you have the ionic bond between this ion, right? Then in details, between the atoms in this ion, between N and H, between N and H in this ion is a covalent bond. Alright. So now, what are their particles in the ionic compound? They will be ions, either cations or anions. Examples we see here. So that one example is similar. You have this example: sodium chloride and ammonium sulfate. Right. Any questions? No. And now let's think about the second type. The second type is a molecular compound. Molecular compound. So let's examine the first question. What elements in those molecular compounds? Non-metals. Okay? But not all non-metals will give you this molecular compound. Okay? So as what we said before, you still use examine that, and I also examine that interceptions. So even though you might have your compound or like non-metals, but if you have that, the kind of very like common example, you can have some example very similar to this. So that's NH4, right? So NH4 all non-metals, and if you see that, even though everything is non-metal, but that will be the interception, right? Good. So that. What bond are in there? What bond in there? Covalent bond. And I also do one interception. I think those interceptions maybe not that important, maybe not that precise, but why not? For my understanding, is so in this molecular compound, and you probably also have those because you have some of those acids. But acid, once you have the acids, they separate. Probably you don't call them. Compound anymore, because in the assay you will see those molecular compounds dissolve into waters. This kind of a mixture. So I will say majority is right. So you still have those photomolecular compound or with the covalent bond. Maybe both. That's is like one like not very common interceptions, that is acid. So we're gonna study acids in the last few sections of this chapter. So then majority just say what kind of particle in those molecular compound, you will say moleculars. But if you think about those acids, because acid is also the so-called molecular compound, but that's kind of special because acid, to be precise, not a molecular compound, and also have to be in some special environment. One special environment in water solvent. Right. So then some of the examples, and here are examples. H2O2, you will see that hydrogen peroxide, so that is a typical molecular compound. And so then this, the other one is sucrose, something like that. So you have the disaccharides, and the formula C12H22O11, and everything here is nonmetals, and you don't have those ammonium in it, and it's not acid, therefore it's a molecular compound. Acids, so we're going to study that in more details. You have that. So you will see the common way to tell you is acid is starting with H, and then followed by the state, which is aqueous. Right. So I think what we can see is that's what I was thinking about, even though the book will not tell you all those all those kind of tedious things. But in case you are just wondering, just so that's what I was thinking. If you don't think that is important, you can forget about those what I write here for the essay. Just think about this metal plus non-metal, or all non-metals, and with the exception that I need for. Right, any questions? So again, if you don't like it, just make sure you study like those similar as what we said in the book. What we said in the book is just classify. We have two different types of compound: ionic and molecular. And that is the important part. For the ionic, and that's what the book emphasizes. For the ionic, pretty much metal plus non-metal, with one exception is that NH4, and the other one vice versa. So that's right. I think that's it's probably a simple problem, but probably make it that like too complicated. So we have this few examples here, and we want to classify them according to what we saw in one slide. So we know we are going to classify them as elements and compound. Okay? So we are going to classify them either as elements or compound. Okay? Now we have two new details. The element has two smaller groupers. The compound has two smaller groupers. Right? One smaller grouper for the element is what? Atomic, and the other one is what? Molecular. So that you studied already. So then the compound is similar, right? Compound is what? Yeah. Molecular. The other one is what? Ionic. It's really a simple subject. Right? So if you know how to classify materials into element and compound, that is very good because this will be our first step here. Right? Then once you get your material is the element, then you examine what's in those materials. So the common example, a common grouper type of atomic element are those noble gases and metals. Right? And then those molecular elements, we have a few examples. I think I give you all together like 9 examples. Sulfur, phosphorus, then that's 7. Right? Compound, if you know your material is a compound, then just tell me in the compound molecular or ionic. What you use let's make it simple. What you do, just say, do you have a metal in it? If you have a metal in it, then you will say it's ionic. But don't stop there. You still want to say, do you have those kind of guy in it? So even though you don't have metal in it, then you examine your second exam. Do you have that NH4? If you have NH4 in it, even though you don't have metal in it, it's still ionic, right? And then the molecules just all those are nonmetals, but also don't stop there. You see all nonmetal, but you see this guy in it, and then you just make the exception. So that's right. Now let's quickly finish this one. So the first one, can you see that from the back? What we have here is xenon, right? So what kind of material is xenon? It's an atomic element because xenon is referring to those noble gases. So usually they are not negative. That means you only have one type of atom. Very good. So that's an atomic element. And what is this nickel 2 chloride? Okay, so that's a compound first of all, right? Because you have a nickel in it, Ni is one element, and they have chlorine in it, so have different type of element in it, so therefore it's not an element anymore. And now we know we only have one formula here, so therefore everything combined into one type of super molecules, different atoms, so therefore the compound, not a mixture, not an element. Right? So that's very good. So you have that metal, and that's good. So that's and what about the C, bromine? Very good. So we're happy to hear that. So that means you know that 7 diatomic, right? So even though I tell you the bromine is a little bit different than I tell you that xenon noble gas, or if I tell you is kerosene. If I tell you it's kerosene, it's also an atomic element. But if I tell you the bromine, so it's still an element, but in details you call that a molecular element. Right? So when we see the next one, NO2. NO2, there's one formula. That means we have a different type of atom. There's only one formula. That means only one possible combinations. What do you call that? Molecular compound. It's a compound first of all, right? Different type of element produce only one molecular. Yeah, so that's molecular compound. What about the last one? NO3. Yeah, so that's also very straightforward. So therefore you have a metal in it, and that's it. So usually you have to examine the second possibility. So you don't have a metal in it, so don't stop at just see the metal or not. Right, now let's do another practice. So this practice is about how do you classify, so which of the following will not be classified as a molecular compound? D is not a molecular compound. Why D is not a molecular compound? Yeah, so it's not a molecular compound, which means you're looking for acid, but no, we're not going to see acid here. That means you're looking for the ionic compound, right? Ionic compound, so what you're looking for is two things. Not only looking for the metal, right? So you're looking for the metal first. If you have metal, then you know it's ionic, right? But even though you don't have metal, and what you're looking for is that what? So for the, let's emphasize for the ionic compound, okay? So we have what you're looking for is you're looking for the metal, right? If you have metal in it, obviously all the others also you already checked. You have to check that not element, not mixtures. So how you get that? So that's a step. You know that the compound metal. So one thing you want to be looking for. The other one is what? Ammonia. So even though I write here just ammonia, but ammonia that means is actually is NH4 plus. So it carry a positive charge. Right. Right. So which of the following is an an atomic element. Right? A. So remember there are two types of atomic elements, two large groupers of atomic elements. One large grouper is a noble gas, right? One large group of atomic elements is noble gas. The other larger group of atomic elements is what? What do you call that larger group of atomic elements? Huh? One is noble gas. That's the one group of metals. Yeah, metals. Metal or noble gas. So this will be the typical element you're looking for. That will be the atomic element. Right? So an exam, mercury is an element. Right? And what kind of material is mercury? Is it metal or not metal? That's the only metal that is liquid at room temperature. Right? What is that's how we started the CRE. So you started all those choices. What is B? What is the NaCl? What kind of material is NaCl? That's a compound. What is that? Ionic compound. Right? Oxygen gas is what type of material? What about diatomic molecular? So you have H2, right? So we have 7 of those diatomic. Right? So this is the diatomic element, and we have 7 of that. Right? What is the other 6? So O2 is one of that. Right? Bromine, very good. So that's Br2. Chlorine, Cl2. Iodine. Yeah. So then you have N2. Fluorine, F2. And there's one more. Yes, hydrogen, H2. Yeah, so these are the 7 diatomic. Di means 2. So these 7, that means you have 2 atoms together. 2 same type of atoms together. Otherwise you become not an element. Right? Alright, so therefore C is the molecular element. What about D? It's a compound, right? They have CO2. There's only one possible molecule or one possible formula, CO2. And let's see, do we have metal in it? Okay, so good. So therefore possibly not ionic, but you don't solve that. Do we have that guy in it? Okay. So we examine for the ionic, we examine metal and what else? This is the so-called ammonium. Right? Do we have ammonium in it? CO2 there, we don't have any N, right? Very good. So therefore, this is the molecular compound. What about H2? Yeah, this is one of those 7 here, right? So that's molecular element, H2, molecular element. Right. Any questions? Okay, so let's continue. All right. This be like what I did, those in that table. Right? So you have to know what the bond in it. Right? For those 2 type of compound, which of the following compound exhibit both ionic and covalent bond? Is it D? Yeah. So in D, you will see this is so in D you have that Na plus, right? Na plus because you have Na in it, right? And actually you have 2 Na plus in it, right? Because you see the subscript here is 2. Right? So therefore the 2, depending on what we do, we can when we write the formula for the subscript, when you write that in equations, you probably want to write that as a coefficient. So then what is the other ion? So this is our cation. So this is our cation. And the other type of ion is what? Anion. Anion is sulfate. Very good. Do you know the formula for sulfate? SO4 2 negative. Yeah. Yeah, so this, when you see those ion, like those sulfate, carbonate, right, nitrate, and so in this ion, as we saw before, so you have S and O and O and O and O, as well as 4O, and this 4O, when S stack together, and then what is the force to make them stack together? This is so-called this bond here and also this bond here, right? So these are the so-called covalent, right? So that's about this. And you can study those in details by yourself. To make sure you can also examine what bond in SO2, what bond in the CF4, right? What bond in NaCl. What about in then I have both ionic and right, you can pretty much say in this SO4 there's only covalent. In this CF4 only covalent. In this NaCl only ionic. And in this one only covalent. Right? So therefore when you study the CI you get study like that. Right? Any questions? Now let's begin to a new topic about write a formula for the ionic compound. If you have an ionic compound, what do you know for sure in it? What kind of particle in your ionic compound? Yeah, metal or non-metal. Metal produces what kind of, yeah, I mean, yeah, so you can either have this ion, right? So ultimately, importantly, what is in the ionic compound, okay? You might have those ionic bond, covalent bond, but if you see your compound is ionic, then you know for sure you will have the cation or anion. So therefore, to write the formula for those ionic compounds, so what do? You will first write the symbol for the metal cation or its charge, but this is only one possibility. Okay? Metal cation, so let me write here. What about that? Oh, that's ammonium. Okay? Because this is by interception. Your compound is still ionic, even though you don't have metal in it. Okay. So to write a formula, so let's do that first. And our example here is the compound between sulfur and strontium. So let's do this first step first. We want to write the symbol for the metal cation and also the charge. Right. So we have two elements here. We have sulfur and strontium. Which one is our metal? Sulfur is metal or strontium is metal? Right, you know that metal in the periodic table is on what side? On the left side. The left side of what? In this table is good because you have this red line here, so this zigzag line. Right? So pretty much the element divide into these two larger groups, and then the division again is not very sharp. So in the middle, first of all, on this side, they are far away from the line, the metals, far away from the line, non-metals. Nearby those lines like boron, silicon, germanium, and arsenic, and antimony, those you call them kind of in between the two, not metal, not non-metal, you call them metalloid. Right? So usually you will not study like that much details, you pretty much those metal on the left side, non-metal on the right side. Right? Right? So strontium is our metal. So what we write here, we are going to follow the first step. I'm going to write the symbol, which means what is the chemical symbol, what are the charge. And I'm going to write it here because finally we are going to put them together. Right? So what is the symbol for strontium? SR. So this is only the chemical symbol, right? Now you're also going to see what is the charge. What is the charge for the ion that is produced from SR? Remember what we studied in Chapter 2 a little bit? For some of those metals, we can predict what are their charge, depend on their position in the table, right? So what do you do? Just use the A group number if you see those metals fall into this type.
Will the metal always be the cation?
Metal by themselves, yeah. So metal by themselves, yeah, in general, metal by themselves will be cations. But cation, what you have to see whether you can predict or not.
Would be SR2.
SR2, why is it SR2 plus?
It's in the 2A column.
Yes, yes, so that's what I want to hear, right? So if you want to predicting for the metals, if you can just use the A group number, right? So it's group 1A, 1 plus, group 2A, 2 plus, right? So why this is 2 plus? Because this is group 2A. And so 2A, 2 plus. Right? Next step, right? Write the symbol for the non-metal anion. Right? So again, if those non-metal by themselves not like fused together, just one type and one atom by itself, it can produce or usually produce anion. Right? So our non-metal in this case is S, and I write in this sequence. I write that positive ion first on the left side, and I will write that negative ion on the right side, and this will be the right way to write the formula. So then we are going to also do a prediction. What will be the charge for one of this ion that comes from one sulfur atom? Remember what we did in the last chapter? We use the group number, right? Which is 6 for sulfur, so here will be our group 6A. So we'll take 6 minus 8, and that becomes negative 2. The 6 comes from sulfur, right? And then this 8 is coming from universal. So no matter what non-metal you have, for Cl, you use 8. For F, you use 8. For sulfur, you use 8. For oxygen, you also use 8. So we will see this 8 more quite often in other chapters, and then you may have a name called octet. So even though sometimes when we talk about that, we probably use some other number, maybe use 2 also, but yeah.
Can you repeat that on chart 2?
Huh?
6 minus 8.
6 minus 8 is for those, so this is the prediction for those monatomic anions. Okay. For the monatomic anions, which means those anions that are produced from only one non-metal atom. So you want to predict what is the negative charge for that. Right? For the positive ion, you just use the group number. So in this example, the positive ion is a strontium. And strontium group 2A, so therefore you just use 2. Now for the negative ion, okay, if you want to predict him, sometimes you don't predict him, just memorize. Okay? So if you have to predict him, just find out what is the group number for that non-metal. So in this example, our non-metal is sulfur, and the group number is 6A. Don't use those big numbers. Okay? Just use, see here, we have the table. On the exam, I will give you a similar table. So you see this 1A, not this H, 2A, 3A, 4A. Okay? So if I give you those tables, you see your elements belong to those group A, sulfur is here, group 6A. Right? So therefore, on this side, first of all, see this line here. On the right side, the non-metal. Non-metal by itself produces the negative ion or the anion. Anion what? That is the formula, that's the pattern. You just take the group number, which is 6A, minus 8. So 8 again will be always 8. Right, so therefore this will be 2 negative. Okay? So we understand that if you want to predict what will be the chemical symbol for Cl, what will be the symbol for Cl? So if you know you will have some of the compound that's ionic and you have a Cl in it, and so then you are predicting the charge for this Cl ion. So how you predicting the charge for Cl ion?
UCl1
You
negative.
want to predict whether it's plus or negative. Okay? If plus that means for one atom there's will be metals. Okay? If there's only one atom non-metal, will be negative. Cl is metal or non-metal? Non-metal, so therefore you know it's negative. Okay? Now negative how much? You use what? You use what pattern? You use the group number or the group number minus 8. So the anion, right? You use the A group number, right? Minus 8. So how much negative? You use A group number minus 8. What is A group number for Cl? 7, you write 7A. But you don't use 8, just use the 7. Okay? So therefore you have 7 minus 8, and that'll give you negative 1. And so therefore you just have this like a negative 1. Right? Predicting what will the ion you can produce from one N atom. From one N atom, what ion you can produce? Okay. Let's see, ion from one N. From one N, what kind of ion you can produce? Positive ion or negative ion? Negative ion, anion, because this is non-metal, right? All right, so we know it will be the anion. Then you predicting negative what? Anion, you use what? Use group number or use group number minus 8? Group number minus 8. Okay? So anion, so again you will use the A group number minus 8. Right? So you use A group number minus 8 to predicting the how much negative. What is A group number for N? Okay, so I will again write something like this. So you have 5A. Right? And so now what do we do? What do we do? We will take a what? Okay, 5 minus okay, so and then that will give us what? Negative 3. Okay. Do that on purpose so everybody will understand. So then what do we put here? Yeah, so we'll just write something like that. And obviously that's only from one N atom. But nitrogen, chlorine, and sulfur, so sometimes they will produce ion by themselves, or sometimes they will combine with some other element. Right? So now let's continue with this problem. Right? So we identify the symbol for both ions. So this will be our cation, this will be our anion. So we finish our first 3 steps. So we get these 2 side by side. Right? So that's a typical procedure. You have to know like what you write first. You write the cation, the positive ion first, negative ion second. Now what you do next is doing this. Okay? You're doing, finish this step 3. So what you do the step 3, we only finish the first 2 steps. You see from there. So what you do for the step 3 is take the number, take the charge number from one ion. Okay? So you want to take this, let's say take this one. First, you write that first. What is the charge number for this cation? What is that number? 2. Okay? So you don't worry about plus or negative now. You have to take that 2. Okay? Now use that 2 as a subscript. When you write a subscript, will be that lower corner, right? So I'm going to take this 2, okay? And let me just change the plane so you will see that. So I hope you will see that. So I will take these two, okay. Going this way, okay. And I will put a 2 here.
It's
It's really large.
Huh?
It's cannot see.
Can I see? I can see it from here. Right, I'm thinking of that. And we'll probably stay with this. So we have these 2, right? So I will put a 2 here. How about that?
Yeah.
That's okay, right?
Yeah.
So that's what we do. That's what we call the switch. We switch the child number, not the sign, okay, onto the other ion. If you have the 2 from one, you get on that for the other. In this example, they both have 2, so therefore you will not see that clearly. But some of the examples will see that clearly. So we do the same, and I will take this 2 here, and put on this here, and we'll have these 2 here. Right, so these are the switch. And so then after switch, you can drop the charge on the top. Okay? So therefore this will become SR2 and S2. Right? So that's the result of our, after step 3, we'll get this guy. So that's simply a switch. You switch the number from 1 onto the other atom. So that's, again, because both is 2, so you will not see that which 2 come from what. So later on you will see that some other examples. Right? Now that's in this. Go to the next step. Okay? So once you have those numbers, and if those numbers come from the switch, that is very important. You only do those numbers that come from the switch. Some other numbers that initially in those formula for the ion, so don't do anything to those yet. Right? So when you have those guys in it, they have some numbers already in it, but those numbers not coming from your switch. Right? So only do those numbers from a switch. Now we have this number, that's good. Most of them come from a switch. So 2 come from a switch, 2 from a switch. Then you reduce them, like what we did for the empirical formula. Right? Reduce, which means you don't have the right, because this is a ratio. So this is a ratio. Right? So right now your ratio is 2 and 2. Right? So 2 and 2 ratio is the same as what? 1 to 1. So therefore we're going to reduce that. So SR and S. And those will be the result of step 4. Right? Step 5, we can do that or not. That's always, if you follow the procedure right, so you know you will get the right sum. So if you want to really do a check, what you do, you will take your answer from step 4. Your answer from step 4 is 1 SR, 1 sulfur. So I have 1 SR and 1 sulfur. Right? So you want to check whether the charge comes out. You will see how many total negative charge you have. Okay? So you will see how many total negative and how many total plus. And for the negative, you will take the number of those negative ions. I write them opposite, because this place is for the negative. Right? So we have 1 sulfur, I just write 1. Right? And then from 1 sulfur ion, what negative charge do you have? Negative 2. Right? So therefore I have 1 sulfur. On 1 sulfur, I have 1 negative 2. 1 times negative 2 gives us total 2 negative, negative 2. Right? So do the similar calculation for the other ion. Right? For the other ion, we have 1 strontium. So therefore I just write 1 strontium. So 1 times. Now what charge 1 SR gives you? +2. So therefore +2. and then all together you have power 2. So that's what the checking. And you just identify in your results from step 4 how many positive ions you have, how many negative ions you have, then review what you get from step 1 and 2, and then you know how many charge for the positive ion, how many charge for the negative ion. So you multiply together, and you should get the same number. Right, so that's right. Now let's do like one more practice. We'll do the lab. So this lab is relatively similar. Right? Now so in this one we'll have a different number for the 2 ions. So therefore, you will see very clearly the switching and also the checking. So let's follow those few steps. We first want to write the symbol for the metal cation, but in general, not only the metal cation. What is the other cation? Metal will give you the cation. If you want to have one metal atom, they will give you the cation. What is the other way you can get the cation in this chapter we studied? The N4, ammonium ion. Right? So in this example, we don't have ammonium. We have 2 elements. One is what? Let me underline these 2 elements. I'm going to change my pen into this one. Right. One is aluminum, the other one is what? Oxygen. Okay. Which one will give you the metal cation? Aluminum. Okay. So you always write the cation first. And when you name that, you also always naming the cation first. Right? Al is aluminum, so I write that first. Next, you already told me the aluminum will produce the cation. Then you just say cation what plus what?
3.
Plus what?
3.
Yeah, so 3A minus 3A. Just read carefully what is the group number for those metals. Al is group of 3A. If it is group of 3A, so therefore we know this metal, so it's a plus, and plus what?
3.
Oh, 3. Very good. So therefore you have this one write first, right? And then you write the second step, which means you want to write the symbol for the non-metal anion. Okay? Well, in general, you will see just write the anion. So sometimes you will see just only one non-metal, sometimes you have a group of non-metals. Sometimes you might even have the metal in it, but that will be the chemistry 1 or 2 or some other chapters. Well, all right, so in this example, what is our non-metal? Oxygen. The symbol for oxygen is O, right? Right. So then you know this will be negative. Negative how much?
2.
How do we know that there are 2? Right, so we take that group number, so this is group 6A. Right? So what you do, you don't worry about A or B, you don't use those B's, you just so this just take just the number 6, so no matter it's 6A or 6. So 6 minus 8 become negative 2. And then you have 2 negative. Right, so that's finished our step 2. Okay? Now this time, our switching becomes really clear. Okay? Maybe here I will change my pen. Okay? For this ion, I will use this color, 2 negative. Okay? Now we will switch. Okay? When you see the switch, you will see that really clear. Okay? After the switch, you don't have to write the chart anymore. Okay? So I will write something like this. AL, in this case I will use both of this color, but the subscription I will use different one. Okay? So I'll take the 2 from the O, and I will put that 2 from the O onto the AL. So I'll put it here. This you can see clearly is our switch or swap. Right? Now I will take the number from the other ion, from the other element. Okay? The other element is AL. The number for AL, the child number for AL is 3 plus. You don't worry about the plus or negative, just take the number, and I will take that 3 and put it onto the other atom. If the 3 comes from that AL, the child number 3, I just put that for the other atom with O. And as I said, this number, you can see very clearly which number comes from what, right? And use in what place. Alright, so that is the result after you switch. Okay? So this is the end of step 3. Right? Step 4, step 5, you might don't have to do anything, depending on whether you have to reduce or not. Right? Right? So step 4 is reduce. What you get, reduce the number you get from switching. Which number you get from switching? 23. Can you reduce 23 into a simpler ratio? Right. So therefore you have that. Now let's check how you check it. So this step, how you check it? You will see how many AL do we have? How many AL do we have? 2 AL. What is the child of AL? So we put that back, right? So therefore I have 2 times what? And I get a plus 6. Right? Now how many O do I have? I have 3 O. What is the child of O? And then I have 3 times negative 2 get negative 6. Alright, so that's it. So let's get ready for the lab. And we'll continue on this next week.
It's so hard to
You can base that. They're up again. Did you pick the,
I hope to be here. Putting water on cakes.
I have trouble with those. It won't open.
I know. You did? I think we should just, maybe we could just do both of those? What you said and what I said, or just what you, I'm happy
I'm
with
just
just what
guessing.
you said. I am too. I mean, that's what they want you to do, is just make a conclusion, and then if everybody did the same note.
Here's stuff with one question, he's not gonna say a lot, as long as you did the experiment, even if it's wrong.
No, because I see the results for other people, not just
We
guessing.
could ask,
what
we
they learn.
could ask the other groups really